First thing we want to do here is check that this is a Hamiltonian system. On the exam, it's possible it might not be. So you need to check. The right-hand side of the dx dt equation is what we typically call f of xy. The right-hand side of the dy dt equation is what we typically call g of xy. We're wondering, is there a function h where this function is the partial of h with respect to y, and this function is the opposite of the partial of h with respect to x? And again, like we talked about last week with Clairaut's theorem, because the mixed second order partials of h in either order are the same, if there is a Hamiltonian function, that's going to mean if I differentiate f with respect to x, meaning the second partial of h with respect to x and y, and the opposite of the partial of this with respect to y, but we'll make the negative signs cancel, I should get the same thing if there is a Hamiltonian function. It also turns out that the logic goes the other way. That's even more amazing. If that condition holds, if the partial of this with respect to x is the same as the opposite of the partial of this with respect to y, then there will be a Hamiltonian function. And that's what you do. Partial of f with respect to x is 1. And the opposite of the partial of g with respect to y is also 1. Happen to be constant functions in this case, but even if these were not constant functions, as long as they're the same function, that would be enough to say this is a Hamiltonian system. These are the same. Therefore, it's Hamiltonian. Okay? How do you find the Hamiltonian function? Well, because these things are found by differentiation of the Hamiltonian function, you can find the Hamiltonian function from them by integration. Doesn't matter which equation you start with. I'll start with the first equation. X minus 3y squared needs to be the partial of h with respect to y. So integrate with respect to y. Integrate x minus 3y squared with respect to y, treating the x as a constant, gives x times y, again treating the x as a constant, minus y cubed. But then don't forget your integration constant, which could depend on x, because we're treating x as a constant when we do this. Call it phi of x. It's not a flow, though. And then you want to solve for phi of x by using the other condition that these two things are the same. So compute the negative of the partial of h with respect to x. Treat y as a constant. Treat y as a constant there. Its partial with respect to x is just y. The partial of that one is 0. The partial of phi of x is phi prime of x. Distribute the minus sign through the parentheses, get negative y minus phi prime of x. What do we want? We want this to equal negative y no matter what x is. Well, the only way that's going to happen is if phi prime of x is 0 in this case. That doesn't always happen. I think in the example last Friday, it didn't happen. That phi prime of x had to be 0. I'm setting this equal to negative y. Solving for phi prime of x. Phi prime of x is 0 in this case. That doesn't always happen. That means phi of x can be taken to be a constant, but I might as well take the constant to be 0. Hamiltonian functions are not unique. They are equivalent up to an additive constant in the end. They're kind of like antiderivatives. But I can take the constant to be 0. So one Hamiltonian function is xy minus y cubed plus 0. You can just leave it at that, xy minus y cubed. So there was a Hamiltonian function. Let's go ahead and jump to using contour plot to help us make the phase portrait. So I'm going to type in the Hamiltonian function. X times y minus y cubed. Make a contour plot of it. Maybe add more contours so we see it better. You can add the option, comma, contours, arrows, say 50 or something like that to add more contours. It's Hamiltonian system. These are the level curves of the Hamiltonian function. Your solutions are supposed to lie on top of those. The Hamiltonian function is supposed to be conserved. The derivative along solution curves with respect to t is supposed to be constant. So for any given initial condition, you're going to be on a certain level curve of h, and you got to stay on that level curve. The only question is, what direction do solutions go? For that, you need to go back to the differential equation. For example, when y is positive, when I'm above the x-axis, dy dt is negative, solutions have to go downward when you're above the x-axis. And when you're below the x-axis, where y is negative, negative of a negative is positive, dy dt is positive, solutions have to go upward. So one thing I know is in this picture, solutions have to go downward up here. So the arrows would have to also point to the left, because that's the only way they're going to go downward and stay on those level curves. And upward down here, the solutions have to also continue to the left up here, or down here, I mean, because dy dt is positive when y is negative. So right off the bat, pretty much, I can tell what the phase portrait's going to look like. Arrows are going to be moving to the left, which means something strange is happening at this equilibrium point, isn't it? It's sort of like a saddle point in this fact that arrows are heading downward here and upward here. When x is positive and y is 0, this is going to be positive. Arrows are going to be going to the right along here. It does look like it's going to be an ordinary saddle point. Can linearization confirm that? Well, first of all, maybe we should confirm that the origin is the only equilibrium point. If you set both of the right-hand sides equal to 0, this one being 0 means y has to be 0. The x-axis is the y nucline. Being the y nucline and being horizontal means solutions that start on the x-axis have to stay on the x-axis. dy dt is 0. This one, setting it equal to 0, when y is 0, means x is also 0. That's enough to say the origin is the only equilibrium point. If you want to draw this nucline, it's x minus 3y squared equals 0. That's equivalent to x equals 3y squared, which is a sideways parabola. That's where dx dt is 0. That has got to get crossed with vertical tangents. Is that clear from the picture? That's maybe not so clear from the picture. I think I'd need more solution curves in here to make it more clear from the picture. If I added more contours, if it would be enough to see. Yeah, you can see it over here. I added more contours. You can see dx dt is 0 right there and right there. There's a curve. The x nucline is not a level curve of h. It's a parabola, a sideways parabola looking about like this. Is what it would look like. I could add it to the picture. Let's add in the stream plot to see it. But be careful. For the stream plot, you're plotting the vector field, not the Hamiltonian function. The Hamiltonian function is just to make the level curves, which happen to be solution curves. But to make the stream plot, like usual, you need the vector field. X minus 3y squared, comma, negative y. There we go. See, those are on top of the level curves of h. And yes, there is an x nucline that's a sideways parabola looking about like this. Could linearization confirm this is a saddle point? It should be able to. It's an ordinary looking saddle point. Jacobian matrix. Partial of f with respect to x is 1. And with respect to y is negative 6y. Partial of g with respect to x is 0, and with respect to y is negative 1. Remember, you always plug in the equilibrium points into this. And something pretty trivial happens with this particular equilibrium point. You get a diagonal matrix. The eigenvalues are the numbers on the main diagonal, plus or minus 1. Definitely a saddle point. They don't have 0 real part. This is a hyperbolic equilibrium point. You can apply the Hartman-Grobman theorem, meaning linearization works, is the upshot of that. And that's what we confirm with the picture as well. This point right there is a saddle point. Once again, it might be good to talk quickly about the corresponding gradient system and the Lyapunov function. We'll take the same function here, but now we'll think of it as a potential function instead of a Hamiltonian function. I'll give it a different name. I'll call it V. But it's the same function. What's the corresponding gradient system for this potential function? dx dt would be the partial of v with respect to x, and dy dt would be the partial of v with respect to y. No negative signs necessary. Partial of v with respect to x is just y. Partial of v with respect to y is x minus 3y squared. Effectively, I switched around the components for the Hamiltonian system and negated this one to make it positive y. If you thought of the right-hand side functions, the vector field, as being vectors that you could take the dot product of, take the dot product of this vector, so to speak, with this vector, you get 0. That's why they're orthogonal trajectories. They're perpendicular to each other every time they cross. The level curves of V are the same as the level curves of H because it's the same function. But the phase plane looks different. The phase portrait looks different. It's a different vector field. It's a different system. The y-nocline for the Hamiltonian system was y equals 0, the x-axis. That becomes the x-nocline for the gradient system, where dx dt is 0. Instead of having solutions that are on the x-axis, they got to cross with vertical tangents. And the y-nocline now is the sideways parabola, x equals 3y squared. You got to cross that with horizontal tangents. Origin's still the only equilibrium point. I won't take the time to try to draw the rest by hand. I will say, if the equilibrium point is a saddle point for the Hamiltonian system, it'll also be a saddle point for the gradient system. If we linearized here, we would get one positive eigenvalue, one negative eigenvalue. Let's just jump right to the picture here. So the contour plot's the same, but I do change the stream plot. Make it positive y and make that the first component. Now it looks like that. That's the corresponding gradient system. The origin's right here. That is an equilibrium point. It is a saddle point. Again, it'd be helpful to also draw in the noclines. That x nocline looks like it's right around here. That's a sideways parabola where dx dt is 0, so you're crossing that vertically. Okay. And notice, being a gradient system, solutions are going from dark to light because the gradient vector always points in the direction that the function, v in this case, increases fastest. What's a Lyapunov function for this? Gradient systems always have Lyapunov functions, though Lyapunov functions are more general than that. They apply to non-gradient systems sometimes too. Lyapunov function is always the opposite of the potential function for a gradient system. Again, the idea of a Lyapunov function applies more broadly. Hamiltonian systems and gradient systems are very, very special. Most systems are not Hamiltonian and they're not gradient systems. They're very, very special. Anytime you have a gradient system like this, the opposite of the potential function is a Lyapunov function. But there are non-gradient systems that also have Lyapunov functions. In general, finding Lyapunov functions is very difficult. It's easy for gradient systems, though. What's the significance of this? It decreases along solution curves. if x of t comma y of t is a solution curve, this derivative should be less than or equal to 0. Yep. Thank you. To find this derivative, once again, use the multivariable calculus chain rule. Take the partial of L with respect to x times dx dt plus the partial of L with respect to y times dy dt. By the way, that can be thought of as a dot product. I don't know if you've ever thought of it this way, but you can think of this as a dot product. Oh, I guess I'm using multivariable calculus vector notation. I didn't mean to do that. It's sort of a habit, using pointy brackets like this. Okay, I could have written them as column vectors. And that's the gradient of L. And this is, well, that's dy dt for the solution curve, which equals the vector field. The dot product of the gradient vectors with the vector field is always going to be, well, we'll see it's going to be less than or equal to 0 for a Lyapunov function. It's 0 for a Hamiltonian function, for a Hamiltonian system. But in this case, what's dx dt? Well, it's y for this example, but that was the same as dv dx, which is the opposite of dl dx. Why? Because L equals negative V. That's why. I'm not using the particular formulas here. I'm using the form of the system. And the partial of L with respect to y gets multiplied by dy dt. Again, for this system, that's that. But more importantly, it's the derivative of v with respect to y, which is the opposite of the derivative of L with respect to y, because L equals negative v. And so what do we have here? We really have the opposite of dl dx squared plus dl dy squared. And no imaginary numbers here involved. This is always less than or equal to 0 for all x and y. So that means along solution curves, L decreases or possibly stays constant. There's an extra condition that the book puts in here that you only want it to equal 0 at finitely many numbers. Or, yeah. We're not going to worry about that condition. Effectively, we're saying L decreases along solution curves. If I made the contour plot for L, just by putting a negative sign in front of the H, it's the same level curves, but now the solutions are going from light to dark. You can see it's light up here and they're going toward darker, and it's lighter here than it is down here. L and H are just opposites of each other. They have the same level curves. It's just that their values are opposites. So where V increases, L decreases. And where V decreases, L increases. Okay. And it's kind of convenient to think of Lyapunov functions in terms of the solutions, the values of L decreasing along solution curves, because it's kind of like you're going downhill. Like the solutions are going downhill. That kind of makes some intuitive sense.